When considering the numerical solution of ordinary differential equations so far, we have been concerned primarily with accuracy and, to a lesser extent, with the efficiency of the method. However, there is a third thing we need to take into consideration, and that is the stability of our solution method. So what do we mean by stability? The stability of a method is determined by how the error at one step propagates at subsequent steps in the computation. If the magnitude of the error at step I decreases as I increases, then the method is said to be stable. We're talking here about an error at one step, how it progresses in subsequent steps. In addition to this, of course, we will be adding new errors every step of the way, but that doesn't really influence stability. If, however, the error increases from step to step, the method is said to be unstable. Note that any unstable technique is always very inaccurate. However, the opposite is not true. It is not true that a stable technique is accurate. Quite often a stable technique can be quite inaccurate. For example, Euler's method. I need to make a note here on what I mean when I'm talking about the magnitudes of numbers, in particular the difference between complex and real numbers here. For all numbers A, whether they're complex or real, the following is true. If the magnitude of A is greater than 1, then the limit as n goes to infinity of A raised to the power n is infinity. In other words, it gets bigger and bigger. If, however, the magnitude of A is less than 1, the limit as n goes to infinity of A raised to the power n is equal to 0. In other words, A to the power n gets smaller and smaller. If A is a real number, then the following is also true. If the magnitude of A is greater than 1, this means that either A is less than minus 1 or A is greater than positive 1. Alternatively, if the magnitude of A is less than 1, this means that minus 1 is less than A is less than 1. For complex numbers, things are a little bit different. So let's write our complex number A as being equal to P plus IQ. Then we can say the following. If the magnitude of A is bigger than 1, what that means is that P squared plus Q squared has got to be greater than 1. Usually written with the square root there, but it's not necessary. If, however, the magnitude of A is less than 1, this means that P squared plus Q squared is less than 1. This is all stuff you would have done in high school, so why am I telling you here? Well, every year in exams, I see students write the following. Oh, we're looking for the magnitude of A has got to be less than 1, and we know that A is a complex number, therefore minus 1 is less than P plus IQ is less than 1. In other words, they have used this formula here for a complex number and not this one. This is wrong. Okay, so I don't want to see this in exams. Okay, let's go back and talk about stability. So we're going to look at the simplest possible example, and we're going to try and determine the stability of Euler's method in the solution of very simple ODE, dy dt is equal to ky, where k is some constant. So if we apply Euler's method to this ODE, we're going to do it I times, but let's just do it once to begin with. We can easily see that y2 is equal to y1 plus hk times y1, where h is the step size that we're going to take. We can see that here we have y1 twice, so let's pull that out and write that y2 is equal to 1 plus hk y1. Similarly, if we go to the next step and calculate y3, it's easy to show that that's equal to 1 plus hk times y2, but we already know what y2 is equal to. It's equal to this thing here, so we can write that as 1 plus hk all squared times y1. And we can calculate y4 and then go on all the way down to yi plus 1, where we can see that yi plus 1 is equal to 1 plus hk raised to the power I times our initial value. Okay, this is only for the solution of that equation, and it's only for Euler's method. So yi plus 1 here is the theoretical value that Euler's method should return when solving this ODE. It's based on an initial value of y1 and a step size of h, and it's assuming infinite precision arithmetic. In other words, no errors are introduced in any of these arithmetic computations here. Be careful, yi plus 1 here is not the analytic solution to the ODE. We know that Euler's method won't give us that. There's going to be errors, but they're truncation errors. They're not propagated errors. In practice, there is always an error introduced in our solution because our computer arithmetic always introduces such a round-off error, basically. So, let's see what happens to an error that's introduced in our initial condition. Let's say that our initial condition, y1c, is equal to the exact initial condition, y1, or the correct initial condition, plus some kind of error. And we want to know what happens to this error as we move forward in our solution of the equation. So after I steps, if we apply Euler's method exactly to this initial condition here, y1c, yi plus 1c will equal 1 plus hk raised to the power I times our initial condition. But we know that our initial condition here is just given by y1 plus our error term, so let's substitute that in. Then let's split these into two terms. 1 plus hk to the I times our initial condition plus 1 plus hk to the I times our error term. This is just equal to the correct solution of Euler's equation with using our correct initial condition, y1. This second term here is our propagated error term. Okay, so that's the theoretical error-free value, and this is our accumulated error. I'm not taking into consideration any of the additional errors that are introduced whilst we're going through this process. I'm only considering what happens to the error in our initial condition, epsilon 1. So, for stability, we need the error term to decrease with time. What that means in this context is that 1 plus hk raised to the power I is less than or equal to 1, but that's entirely equivalent to 1 plus hk. The magnitude of that must be less than or equal to 1. In actual fact, for the error to decrease, that must be a strict less than. So therefore, this is a real number, 1 plus hk is a real number, therefore we can use the formula negative 1 is less than or equal to 1 plus hk is less than or equal to 1. We can subtract 1 from all of this equation to give us minus 2 is less than hk is less than or equal to 0. And finally, we can divide by k to give us minus 2 on k is less than or equal to h is less than or equal to 0. Now, in order to do this here, k must be a positive number. Okay? We'll come to what happens when k is negative next. So, for any positive value of k, this condition here states that the Euler solution is unstable for any positive value of h. So if h is positive, h cannot be less than or equal to 0. That's not possible if h is positive. So therefore this is unstable. And it's unconditionally unstable. It doesn't matter what step size we take, the method will never satisfy this condition here. As an aside, the error also will grow more rapidly as our step size gets bigger. Okay, so let's go back to our stability condition. What happens when k is negative? Well, in order to investigate this, to make sure we don't trap ourselves up, let's let k equal negative c, where c now is a positive number. So we replace this by 1 minus hc is less than or equal to 1, where we know now that c is a positive number. So this then gives us negative 1 is less than or equal to 1 minus hc is less than or equal to 1. Again, we subtract 1 from both sides. We divide through by c, and we just swap things around a little bit, and it's very easy to show that 0 is less than or equal to h, is less than or equal to 2 on c. So h being greater than 0, not a problem. But we also need h to be less than or equal to 2 on c. So, for any negative value of k, this condition states that the Euler solution is stable provided h is less than or equal to 2 on k, or 2 on mod k, sorry. That's exactly equivalent to this condition here. So we can find stable solutions provided our step size satisfies this condition. This is termed conditional stability. In other words, it will be stable, but there are some conditions on the step size that we can take. And just having a quick look at a particular example, for example, dy dt is equal to negative 12y. This condition, we derived on the previous page, suggests that h is less than or equal to 1/6 will be a stable solution. What happens when we try and find this solution when we choose a value of h that's bigger than this is we get an error very rapidly increasing. However, if we choose a value that's less than 1/6, we can see that the error decays. And in actual fact, there'll be a point defined by h is exactly equal to 1/6 where we have what's called neutral stability. In other words, the error doesn't get bigger, but it doesn't get smaller. Got to be very careful operating around that region. So everything that we've looked at so far assumes there is an error in the initial estimate for y. We then go ahead and consider what happens to the error as we go forward in time, or in space if we're integrating in space. And we ignore the additional error that's introduced with each step. This is clearly incorrect, but it doesn't really make much difference for stability. The example in the previous slides is only for this very simple ODE. dy dt is equal to ky. What happens for other ODEs? Well, let's look at Euler's method again. So yi plus 1 equals yi plus hf of ti yi. So this is the generic case where f can be any function now of t and y. As before, let's assume there's an error, epsilon I, in our solution yi. The question then is, what error does this lead to at level I plus 1? In other words, what is epsilon I plus 1 in this expression here? So we're saying yi plus 1 is equal, plus some new error term, we don't know what this is equal to the old or previous guess plus the error at the previous time plus the function evaluated with ti and yi plus the error that we previously had. Let's expand this last term here in a Taylor series about yi. So this gives us this thing here. H times f of ti yi plus epsilon I df dy plus some higher order terms in the error. We subtract the exact Euler step, so I've just rewritten the exact Euler step here, so y1 minus y1 is 0. So we're going to be left with epsilon I plus 1 on the left hand side, yi minus yi is 0. We're going to be left with epsilon I plus, that term will cancel with that term, epsilon I df dy. Oops, so that was a bit careless there. Let's just write that out again. If we subtract that, we see that the error at time I plus 1 is equal to the error, at step I plus this term here, and we're going to ignore the higher order error term. So let's just take epsilon I at the front here, and we're left with this expression here, that the error at the new time is equal to the error at the old time multiplied by 1 plus h df dy. Therefore, the magnitude of the error decreases in Euler's method provided the magnitude of this is less than 1, and this is a real, well, we're only going to be dealing with real equations here, which then gives us that minus 1 is less than 1 plus h df dy is less than 1. Subtracting 1 from this entire expression gives us minus 2 is less than h df dy is less than 0. So, let's consider a concrete example. Let's consider the case of dy dt is equal to 12y squared. Stability, as we've just derived it, using Euler's method, requires that minus 2 is less than h df dy is less than 0. So, if f of t and y is equal to 12y squared, df dy is equal to 24y, and this condition becomes minus 2 is less than 24yh is less than 0. Now it doesn't make sense to talk about negative step sizes because nearly always we're integrated in a positive sense, usually positive in time. So we want h to be greater than 0. If h is greater than 0, then 24yh is less than 0 means that y has to be less than 0. And also, if we look at the other side of this condition here, it's easy to show that h has to be greater than -1 on 12y. So, in this case, stability is a function of our solution. The solution is actually y itself. And it's possible this can change in mid-computation. So if y starts off as negative, when it becomes positive, then all of a sudden we can't satisfy this condition here and the solution becomes unstable. Complicated ODEs will have correspondingly complicated stability properties. Also, we're just considering Euler's method here. As soon as we start moving into other methods, it becomes much more difficult to find out what's going on. So for example, in the fourth order Runge-Kutta method, the equation for stability is equal to this expression here. So minus 2.78 is less than h df dy is less than 0. We're not going to attempt to derive that. It is too complex.